Good day, I'm Dr. T and welcome to my office. Today I'd like to talk about density. Density is a description of how much matter, the amount of stuff you have, is within a particular volume. And the idea here is that a lot of different substances, depending on the environment that they're in, things like temperature and pressure will change this, but we'll have a fairly characteristic density, and this can be useful to us as chemists doing a few different activities. For starters, and one of the things as chemists we generally don't do, but you can actually use this to find density if you wish, is looking at things like buoyancy, a little bit more of a physics approach. For something to float in a fluid, so a fluid would be either a liquid or a gas, or a couple other quirky individuals like that. But in order to float in a fluid, then one needs to be able to displace one's mass of the fluid. So if you've got a boat, the boat floats in the water, as long as it's able to push an equal amount of mass of water out of its way. Now, if your density is less than that of the fluid, you will be able to do that, and you'll still have more of your product left over on top of the fluid to continue floating. But if your density drops below that of the fluid, then by the time you have pushed your volume out of the way, you still haven't pushed enough of the fluid out of the way for you to continue floating, and thus you'll sink. So the thing with the lowest density is going to be the one that floats on top. Obviously, if you have a solid like a boat floating in a fluid, then you get the basic idea, but you can also have two different fluids. This is why things like warm water tend to rise and float on the surface. They have a lower density. Generally, when things are warmer, they expand and their density goes down. So this is me from the future. While editing this video, I realized that there were some omissions that I probably should have talked about with buoyancy. While buoyancy is a classic physics thing and more of an engineering suit, especially for those folks doing, say, boats and whatnot, we do use this as chemists as a couple of interesting scenarios, although we don't really think about it as buoyancy. One technique we use is to take two solvents. These are usually liquids, they don't technically have to be, but usually liquids that will make solutions, they'll make mixtures. We pick two of them that won't mix with each other, what we call immiscible. Now, if we've got chemicals in one of them and we shake them up, the chemicals that prefer the other one will tend to hang out with the other one. But because these two don't mix, they will separate. They become two layers with the lower density one on the top. This allows us to move chemicals around, separate chemicals in what we call liquid-liquid extraction. It's a quite useful technique, and relative densities tell us which chemical is where. We also have to worry about chemicals that would normally mix, specifically gases usually in this case. If you don't agitate fluids, they may not mix. Actually, the passive mixing of fluids is very slow, and this is usually relevant to gases because you can get layered gases. Now, if it's in a beaker or something, that's kind of cool, but if it's in the area where you're breathing, then one of those gases might be air. It might have enough oxygen to sustain life, but you could have an imperceptibly different layer of gases, so you can't see it, you can't feel it, you can't smell it, but at a certain layer there's a different gas there that may not contain oxygen, or a good chance doesn't. This is a particular problem in certain volcanic regions, specifically around the Great Rift Valley, where carbon dioxide is coming from within the Earth. It builds up, but it's coming up slow enough, and if you don't have a good breeze, it can pool in depressions on the ground. Now, if you walk through it, as long as your head is above the layer of the carbon dioxide, you won't know anything happened. But if your head is below the layer, or so I say you're small, aka a child, or maybe some livestock, then instead of breathing in air with it's 21% oxygen, you're instead breathing in a pretty high purity carbon dioxide, which is poisonous. Not only does it not have the oxygen, the carbon dioxide itself is toxic at high concentrations. Additionally, in the lab, we have to pay attention to what gases we're generating if we are generating toxic fumes and how our ventilation works. If we have ventilation that pulls more or less exclusively from the ceiling and we produce a heavier than air gas, we're not getting rid of it. Likewise, the reverse is the case. If we pull from the floor, we're producing a lighter than air gas, which is relatively uncommon, but they do definitely exist. Then once again, we're not actually getting rid of it. So we've got a couple of considerations to do here. The other one I want to bring up is that with mixtures of chemicals, which normally we can't do dimensional analysis with mixtures of chemicals. And density. We can do dimensional analysis with other things, but we can relate density to the concentration within your material. The more stuff you have in your solution, it will change its density depending on what the stuff is, depends on which way it will go. So for things like alcohol brewing and concentrated like sugar solution, so good old-fashioned maple syrup, then the way we monitor concentration is quite often how high a floater floats within those, and thus giving us another tool. That's not really something that a classic chemist does. That's more of a brewer's, or whatever you call someone who makes maple syrup, doing. But we are definitely dealing with chemistry here. It's just more of an applied side. Back to the regular video. Now we can use density in a couple other approaches. Under, once again, a standard set of conditions, things will have a characteristic density. And while there are definitely things that have the same density as each other, if the density of an item is not what it should be for what that item is, then you know that there is definitely something going amiss with this. And this goes back to a probably not true story, but it's also too good not to tell. This story goes that there was an ancient Greek king, and this king had a problem. He had commissioned a crown, and so he had got his fancy new hat, and he was all excited, but then there were whispers. The whispers were that the goldsmith had embezzled. Instead of taking the pile of gold the king had given him and making the crown out of it, the goldsmith had taken a pile of gold, taken some off, put it to the side, and taken some lead and mixed it in with it. It looked identical, the king couldn't tell, but if the goldsmith had stolen the gold, had embezzled, then the king had a problem. If people started believing that they could embezzle and defraud the king, his power would be gone, his days would be numbered. Likewise, if the goldsmith didn't embezzle and he punished the goldsmith, then it would become well known that one could lie about your opponent and the king was so gullible he would believe him. Well, the king needed to make sure he punished someone, and he needed to make sure he punished the right person. So he goes up to the smartest guy in the town, a guy by the name of Archimedes, and tells him, hey, I got this problem. So I'll be willing to give you a small pile of gold if you can tell me which one, and if you can't, well, I need to chop someone's head off. I don't really care whose, yours will work just fine. So Archimedes, wanting some gold and liking to keep his head, decides, hey, he wants to figure out density. Now, density is an item's mass divided by its volume, or its weight divided by its volume, although that is an imperfect system because it relies on Earth's gravity. So he decides, okay, I can weigh things very easily. It would be very easy to weigh the crown. At this point in history, this is, of course, a few hundred years BC, we had good scales. They weren't as great as today's scales, but they were still perfectly good. So Archimedes is like, okay, I can weigh the crown. All I need to do is find the volume. And now the Greeks had come up with wonderful mathematical equations to find the volume of regular shapes, but the crown wasn't a regular shape. And he couldn't destroy the crown. He couldn't beat it into a sphere or a cylinder or anything like that because it was the king's crown. You can't just go destroying the king's crown. Then in that case, the king's going to chop his head off either way. So he has to find the volume without destroying the crown. And the story goes that being kind of stressed, he wants to chill and kind of think about what's going on. So he decides to hop in the bath. So he draws a bath, hops in, and notices the water overflows. The water had gone up, and had gone up by his volume, by him going in. And thus came the idea of displacement. You can take an item that sinks, and it has to sink in this case, drop it in a fluid. The fluid's volume will go up by the volume of the thing you just put in it. And if you have the fluid in a container that you can measure volumes with, bada boom, bada bang, you got a volume. And it doesn't have to be a nice regular shape because the container, that could be a nice regular shape like a cylinder. So we've got a couple uses for density. We can identify the item we have, or at least rule out items. If the density matches, in this case, we haven't actually proved that it is. It's just something that has that density. If the densities don't match, then you know good and well it's not gold, and you got somebody's head to cut off, or hopefully fine, or we're a little bit more gentler these days in chopping people's heads off. Now, there is a third use, and it's actually what, as chemists, we tend to use the most of. Density has two units. For fluids and solids, or I should say for liquids and solids, it's usually grams per milliliter. So we have a top unit that is going to be a mass unit, and that's usually grams for dense things like solids and liquids. And then a bottom unit, which will be a volume unit, traditionally milliliters. For gases, it's going to be grams per liter. Gases have a much lower density, so it's useful to have a fluffier unit. So grams per liter, you need the full liter to get up to a few grams. We can use this because there are two units as a conversion factor. So we can plug that into dimensional analysis. We can take something like, say, 500 grams of a substance that has a density of 5 grams per milliliter, times 500 grams by 1 milliliter divided by 5 grams. Because what you do is you take your density, the number goes with whatever is normally on top, and since I want the thing that I have to be on the bottom, it's what you want divided by what you got, and what I've got right now is grams, I'm going to put the grams on the bottom, and that means the number goes with it. So 500 divided by 5 tells me that I have 100 milliliters of whatever this stuff is. Likewise, if I had, say, 10 milliliters of this stuff, 10 times 5 grams over 1 milliliter would give me 50 grams. Yay! And this is actually the key use that we use it for. So you'll quite often see density used in dimensional analysis equations. You're going to start off with, say, volume, and you need to get to grams, or vice versa. Now, this only works with pure substances. When you have mixtures, we're going to learn a different set of equations, because in that case, it's not one thing, and it's a bit more complicated. So we have to use things like percents or molarity, etc., which we will cover in later units. With that said, have a wonderful day.